Um, it's a pleasure to introduce Igor Aharonovich today, who's going to give us a seminar. So Igor, if I can remember correctly, got his PhD in Melbourne with Stephen Prower, and did a postdoc at Harvard, and then came back to Australia to University of Technology, Sydney, where he is now a full professor. And he, part of his work at Sydney has been on 2D materials, where he discovered a room temperature quantum emitter in hexagonal boron nitride, and a number of other amazing things that he's going to tell us about today. And in his talk about quantum nanophotonics with hexagonal boron nitride.
Thanks, Michael. Yeah, good morning, everyone. Great to be here. We were just discussing if I was here before or not. I think maybe a few years back, BC, before COVID times. Yeah, so today, I guess in the next, I don't know, as long as you are awake, basically, just gonna show you our kind of most recent results on quantum emitters in boron nitride and our exploration of this material. It turned out to be quite an interesting and a unique platform to study basic light matter interaction. So it's going to be divided into some few topics. So hopefully we can all stay together for this. And I was just thinking to start with this slide that I found online a few weeks ago. And this thing says, 5 ways to use quantum technology every day. And the slide is very interesting because, with all this quantum hype, everybody is now doing quantum, but actually none of these things that you see here is actually using anything quantum really. So you really need to know quantum physics to explain a lot of this phenomena. GPS, of course, they rely on two-level systems, some of these aspects here, but they don't really harness the true quantum effect, the true kind of phenomena like entanglement, for example. And so then I thought, well, okay, let's look at some roadmaps that people put together. So this is from the European Union roadmap that they want to develop, atomic clocks and quantum sensors and eventually a universal quantum computer. This was, 2015, a few years back. And this is their deliverables. And you can see here that you should have a quantum credit card within 5 to 10 years, which is pretty much now. Hands up who has a credit card in their wallet, probably not yet. And I guess the reason why I'm saying this is that the results I'm going to show you today, they're not going to be really used as a quantum hardware in the next 5 years, but they're really an exploration and a curiosity-driven research. And I think it's very important for all of us to kind of be on the same page with how much is our research is kind of technologically ready and how much is it really curiosity-driven. And I really want to make sure that we're on the same page and that the results I'm going to show you are really kind of curiosity-driven. There are many questions that we still don't understand about the system, but it's really offers kind of a lot of interesting opportunities to explore. So if you look back into some very famous people that wrote excellent reviews on what do you need to do to realize quantum internet or even very basic quantum network, you need a few components, and this is basically an individual quantum system that you can manipulate and trigger and control. So for example, a single photon source at some point. And you will use, for example, photons to communicate between your nodes, and every node would have some sort of a cavity to really help you to interface between light and matter. And so if you think about what's the best quantum system you can imagine is, of course, a single atom or a single ion. And really, people like Gerard Rempe from Max Planck, over the last few years, they really did fantastic work on trapping these individual rubidium atoms and really demonstrating fundamental constituents, fundamental kind of hardware components of what is to be a scalable quantum network. And so here is an example of, let's say, the 2 rubidium atoms that are interconnected 60 meters or so. And it's basically a very kind of fundamental quantum logic gate that you can build with these 2 trapped atoms. Now, you can take this further. So this was more recently from the group of Harald Weinfuter. This is a heralded entanglement, which means that it's not a probabilistic where you just wait for the events to occur. You really prepare the system deterministically, you trigger them, and then everything is done over a large distance. So this is over a few kilometers already. And this is kind of, again, the first deterministic demonstration of an interfacing 2 quantum systems together to demonstrate entanglement. Now, of course, you want to scale it down to have it on chip, right? Because not trapping ions, of course, the technology evolved a lot, but ideally we want to get into something which is in a solid state. And this slide, this I stole from the University of Rochester, and they kind of envision how is it going to look like, and you would need some sort of waveguides and some sort of kind of cavities to trap your single photon sources or your atom, whatever you choose to work with. And then, of course, you would need some sort of manipulators and heat sinks, etc., etc. And so our expertise and our interest lies within the quantum light sources. We don't do much with memories, but of course you would need one. And we don't do much with, let's say, kind of entanglement distribution, which is, again, a separate issue. So what is a single photon source? Just to kind of get us on the same page. So it's an isolated quantum system, basically an artificial atom in solid. And there are two types of solid state sources you can imagine. Most of you are probably familiar actually with both of them, but you can think about your kind of detuned from the valence and the conduction band. These are your typical quantum dots that have been around for many years. So you just introduce a slight energy detuning, and then you have a trapped quantum dot, and it will emit single photons, typically limited to cryogenic temperatures. And if you go to wide bandgap materials, are your color centers. So they would have a ground and an excited state very deep within your bandgap. So in this type of systems, you would need maybe 4 or 5 eV bandgap materials, which makes the research kind of fascinating. It also makes it very comfortable because its first-year student can go to the lab, pick up a diamond, drop it on the floor, pick it up, put it back in the confocal microscope, and everything still works, right? You don't need to operate dilution fridges or cryogenic fridges. Although, again, the technology is evolving, obviously. And to know if you're actually emitting a single photon source, you would record this anti-correlation measurements or anti-bunching measurement, and it will look like something like that. Just the lack of coincidence here means that you're only getting one photon at a time, and that's the evidence. And you would see this measurement on almost every slide in our presentation because this is our bread and butter. So the students basically recording these anti-correlation measurements almost every day. Okay, so if you kind of reverse time and look back to history to, let's say, about 2007, which in scientific terms is not actually that far, you really only had 2 systems available for you. You had your self-assembled quantum dots, and even back then, you know, Imamoglu, Yamamoto, Peter Mikler, Andrew Shields have done already a terrific job, and there are many others here. You could already generate indistinguishable photons. And of course, you had the NV center in diamond, which was a single photon source, but the prime interest there was for sensing, and we'll talk about it at the very end. Now, if you fast forward 15 years, now actually the choice of single photon sources is quite large. So in reality, there is no problems anymore to find a single photon source. You just need to specify which wavelength do you want and what material do you want, and you will get one. And so there is a lot of defects in carbon nanotubes and single molecules, even perovskite crystals. Of course, the research into quantum dots really skyrocketed, and there are many, many groups. There is a beautiful review from Pascal Senelard, who is actually selling those sources now together with a cryostat. So if you want one at your home or on your desk, you can ask your supervisor to buy you one. It's a few $100,000, but you can get them on demand, emitting at about 900 nanometers. And of course, our interest is in the scalar centers, which are these deep defects within the band. And so then when you look at which material to choose, of course, diamond has a about 5 eV bandgap, but you can also choose hexagonal boron nitride, and it has a 6 eV bandgap. Actually, very interesting about hexagonal boron nitride that the bandgap was always thought to be direct bandgap material, but actually it's an indirect bandgap material. But for color centers, it's not actually that important because we don't go, I remind you, from the conduction to the valence band or vice versa. We're really trapping defects very deep within the material. And so there are actually also more interesting stuff to do with boron nitride. Obviously, it's a layered material. It's the only wide bandgap material that is also a layered material. So you can think of many, many different applications where you can just peel off your material that has the single photon source and really put it somewhere, wherever you like, for example, as a sensor or on your integrated photonic chip. And very recently, there was a lot of work on twistronics. And actually, there is also an effect even on the very deep defect within the HBN if you twist 2 HBN crystals, which is not intuitively because from the superconducting work on graphene, you would think that it only influences the bands, right? But that actually doesn't. It also influences what's happening within your crystal itself with the very deep defects. So this was kind of the motivation when we started. And I guess before I go into our results, I want to show you two very nice works that I personally really like about HBN and really what makes it unique, unlike other 3D systems that would have also single photon sources. So the two works here, one of them is from the group of Shalaev, and here they actually show that if you exfoliate a very thin HBN, you can really go with an AFM and scratch it, really physically scratch it, and everywhere you scratch, you would generate an emitter. And that's something that you cannot really do with any other material. If you just go and scratch your silicon carbide, you're not going to see anything. And the second work is from the group of Stefan Hoffman in Cambridge. What they did is they took an HBN that has no single emitters, just a very broad ensemble, and then they put a graphene on top and below and quenched everything else, because graphene is a very good source of non-radiative energy transfer, so you just kill everything else. But what they did is they patterned the graphene. And so what you get as a result is basically an array of single photon sources, not because you implanted them, but simply because you patterned and made holes in graphene that basically then allowed this emission to survive. And so this type of tricks you cannot really do with any other 3D system. And this is really makes the HBN as a very unique platform in this regard. Okay, so today, I guess I will show you cryogenic spectroscopy in our attempt to get indistinguishable photons from HBN. We haven't done it yet, but towards. I will show you then a new family of blue emitters, and then maybe some spin defects, and then we can go for lunch. So obviously, the motivation, of course, is to get indistinguishable photons. Now, before we get there, we need to kind of engineer the emitters. And so I'm just going to reference here most of the work. Some of it is ours, some of them are not. But we can now grow HBN on the kind of people in the semiconductor industry say wafer scale. We say copper scale because it's just on copper. You buy copper and you heat it up to about 1,000 degrees and you grow HBN. The material quality here is very low. Okay, it's all polycrystalline, very small grains, but for single emitters, it's actually quite good. So we have a lot of emitters, and most of them emit at 600 degrees, 600 nanometers, and most of them have this signature of an anti-bunching. You can also localize it by growing on pillars. This is on silicon oxide. So after a few years and following a few established recipes, you can basically grow HBN on anything you like, and you will get single photon sources. Now, at room temperature, they don't mean anything. So how do they behave at a low temperature? So for that, we really need to go resonant excitation. So typically we excite with a green laser, as I mentioned, just going to some 2.4, 2.5 eV to get the defect. For resonant excitation, we really excite exactly the same wavelength. So for our emitter that emit at about, let's say here, 600 nanometers, we bring in a tunable laser, we park it right at the resonance of the emitter, and we trigger it. And so the collection is quite challenging because you only can collect then the phonons, the phonon sideband. You cannot really collect cross polarization yet. It's a bit more complicated, so we collect the phonons. And so what you see then is that the emitters, this is our best result. The emitters are about 1 gigahertz broad. If you compare it to the natural line width, they should be around 100 megahertz. So that's your lifetime of about 3 nanoseconds. So inverse of that should give you about 100 megahertz lines. So we are 10 times broader, not good. And you can also see that this type of lines, you only get at low excitation power. So this is nanowatts. If you increase the excitation power, you will observe the spectral jumps, all called spectral diffusion. And that means that the system really going to the excited states, and then there is a random Stark shift. You spectrally diffuse, then you excite again, you spectrally diffuse. And that's very not ideal because after the first scan, you basically have no emitter. So you scan with your laser, you excite it, you get a photon, and then it's being kicked out to a different frequency. So this is something that you want to avoid. How do you avoid it? Well, intuitively, one would think if this is all depends on fluctuating fields, you can apply a field and stabilize the emission. And with 2D materials, applying a field is easy. You just make a device. And so we did. So this is our HBN emitter layer, and we cap it with another layer of HBN, and we put graphene on top. The graphene on top is just to provide the contact. So that's our kind of top gate or top contact. And that's all on silicon. Now here, the results were surprising. So when we applied voltage, we didn't see any stabilization. However, when we just scanned around on areas that we did not see any emission, when you suddenly turn on the voltage, you see an emission. Now, this is not electroluminescence, okay? Not electroluminescence. The laser, the green laser is always on, but in addition, we also turn the voltage. And you can see that the process is very reproducible. So the voltage is on, you have emission, voltage off, no emission, on, off, etc., etc. And you can see example here. So the black curve is a dark spot that has no photons. Once you apply voltage, you suddenly see an emission, and it's a single photon source. Okay, so it's kind of a cheeky or a tricky measurement to do because you don't know where you see it because there is no counts on the detector. So you're just blindly looking where there is no light, and then you turn the voltage on. Okay, but the device is quite small, so it's easy to do. 1 hour, you map the whole thing. So what is happening? So for this, we took an HBN with a very high density of emitters, and what you see here is basically a spectral map of many different emitters. So every line here is a single photon source. It's all done at 10 Kelvin, so the lines are very narrow, few nanometers, and you can see what's happening. So at zero delay, at zero bias, there is almost no emission, which is here. As you increase the bias, let's say you go to 10 volts, you start seeing some emitters, and then as you increase the bias more, they all disappear. And that's reproducible. So let's say this emitter turns on at about 20 volts, this emitter turns on at about 30 volts, etc., etc. So every emitter turns at random voltage and then goes off. At the negative voltage, you see an opposite effect. You see that the emitters just gradually turn on. So this one is on brighter and brighter, brighter and brighter, etc., etc. Now, here, there are two important things. One is that we don't know which wavelength are we imaging a priori. We just put a sample with many, many emitters, and then we turn the voltage on. And number two is that, remember that every emitter turns a different voltage, but we don't know which one will turn at which voltage. Okay, so that's we can't control that. It's all the result of the actual experiment. So how do we explain that? So to explain that is we can draw a proper level diagram. So this is kind of the level structure of the device. So we have about 4.6 eV to the vacuum from the graphene level here, and we have two charge transition levels of the emitters and the Fermi level of the junction. The device is to scale, so we have 20 nanometers capping layer and 20 nanometers layer with emitters. Okay. So then when you apply positive voltage, you will see that one transition level crosses the Fermi level, so it will become optically active. And then when you increase the voltage even further, the second transition level will cross, and this transition level is not optically active. So it's basically a charge switching effect. If you look at charge switching of NV center, NV minus and NV0, both optically active, but it doesn't have to be. So in the case of HBN, one of them is active and one of them is not. And so this is why when you increase the bias, some of the emitters goes off. And as a function of depth, where the emitters are located within this level, of course, your slope will be different. And that is why some emitters turn on at 5 volts and some of them turn on at 15 volts. Okay. And the negative bias, you would have a different effect. So you would have a hot electrons going to the conduction band of HBN, and under very strong bias, they would basically propagate and recombine always at that defect. Now, this theory is very easy to check because you can change this excitation wavelength. Remember, we excite with green laser, so it's about 2.3 eV. So we're going from this Fermi level to the conduction band here. If we now change the laser to, let's say, red, much lower energy, then you should not see anything. And so that's indeed what's happening. So this is, you sit on an emitter here, you excite with the green laser, it will turn around minus 20 volts. When you shift the laser to red, to 600 nanometers, which is less than 2.4 eV, you don't see anything. This is just a Raman. So you sit exactly on the same confocal. So it's a nice kind of theory. We have absolutely no proof that this is actually what is happening, but all the kind of the ducks align basically. So it looks legit. Now, why did I waste your time telling you all that? Well, if you look back in the literature, actually, what's happening is that in silicon carbide, for example, this is the work from the group of David Avshalom. What they do is they create PIN junctions in silicon carbide. Yeah. And what they do, they apply negative bias. And under negative bias, they create a depletion level. And when you have depletion level around your defect, there are no fluctuating charges. Remember, the goal of the whole exercise was to eliminate these fluctuating charges. We were just hoping to do it by just a bias, but it didn't work. So in their case, it actually works quite well. They eliminate the charges, and then you get very narrow lines. This is about 30 megahertz, basically Fourier transform limited line. So if you take the analogy to our case, we of course don't have a PIN junction, but under very negative bias, we do have a depletion layer, essentially. So under negative bias, we can look at the emitters, and they are very stable. The line width is spectrometer limited when you pump off resonant, and when you go on resonant scan, you really get this 160 to 100 megahertz lines, which is basically Fourier transform limited lines from these emitters. So this is a way to engineer your single photon sources in HBN. And if you make them into these devices, you can actually get them Fourier transform limited lines and hopefully then generate indistinguishable photons. We haven't done the indistinguishability yet, but this is now stable and reproducible. And I also would like to mention here, there's a beautiful work from Agubari here on arXiv, and they actually did the same thing with the device, and they also saw that when you increase the bias, you have these lines become much, much narrower. So it's a very cool effect. All right, so kind of shifting gears towards what can you do with these emitters now. So obviously we have a 2D material, so I will just show you one result of how we can then integrate these emitters with some sort of a waveguides or a photonic crystal cavity. This is kind of the vision of how we want to do it. Many waveguides, and then you put HBN on top, hopefully with identical emitters that you will generate on cheap, basically indistinguishable photons. So how do we do it? So as I mentioned, we can grow using CVD, very high density of emitters. So we grow our HBN flakes and then we transfer them onto silicon nitride. The reason why we choose silicon nitride is because silicon nitride is very easy to fab. And when I mean easy, I mean that it takes, the recipes are well established. You go and you etch your photonic structures and the success rate is quite high. And the undercutting is relatively simple. And so you can then deposit your HBN and do EBL and pattern your devices with the HBN on top. And so this is how it looks like. So this is a 1D photonic crystal cavity that is made from silicon nitride, and it has HBN already on top. Okay, you obviously cannot see the HBN, but it's there. This is an optical image of the same chip. So this is with the HBN, that's the HBN, and this is without the HBN here. And every line here is basically one of those photonic crystals. And so there are a few take-home messages here. And the most important thing is that the HBN doesn't actually degrade your quality factor. So typically in the photonic crystal realm, if you put something on top or if you don't make it perfectly designed, your quality factor will degrade. In our case, it's actually the same. So the red lines here, there are not emitters. This is just a resonance of the cavity that we control around the 600 nanometers. And you can see that with and without HBN, the quality factor is nearly identical. So it is around 3000 or so. Yeah. So for the visible range in a 2D hybrid materials, not too bad. You can, of course, go to silicon photonic crystals in the IR, get much higher Qs, but for our case, not too bad. Also, remember that the model volume here is very small. It's a 1D PCC. Now, the trick that you can play is you can actually make the thickness of the silicon nitride cavity a little bit thinner, maybe by 5 to 10 nanometers, and then the HBN layer will actually cover the cavity and will complete your cavity. And this is nice because then your mode leakage here from the cavity would leak further and will interact stronger with the emitter. So we are still in the coupling mode. It's still in a evanescent coupling where the mode is leaking. That is what is coupled to the emitters, but it's leaking kind of, you have more leakage than if you would have designed a purely silicon nitride cavity and then put something thick on top. Okay. So does it work? It does. So because we grow very high density of emitters, basically every spot would have an emitter and almost every spot would have already coupled system. So this is one example. So you can see here a very bright spot in the confocal map. This is actually already an emitter with a cavity. The Q here is about 2500. You can actually decompose the emitter and the cavity mode. And this is an anti-bunching measurement. And the student who now graduated and is having a postdoc. So Johannes in a very good place in the US. He was so surprised that he saw this from the first go that he stopped the anti-bunching. You can actually count the number of clicks on the detector. It's about 15 after 15 seconds because he didn't believe that it's actually working. So it is working pretty much on every cavity. The challenge is, of course, is with blinking. So what we found along the way in this kind of journey is that emitters on silicon nitride actually blink a lot. And the same thing happening on any silicon-based substrate. We don't actually know why. We tried capping and stuff, doesn't really help, and we cannot cap underneath, remember, because the cavity is coupling evanescently to the emitters. Our emitter should really be close to the cavity. So we don't really know what's happening, but this is one live result. So this is basically as found an emitter, the cavity mode is here and the emitter is this broad thing. This is a random shift. You see it's coupled perfectly. Then the emitter goes to the other side and then it bleached out. So that's still the cavity mode. So we don't really know how to solve it just yet. If anybody has any ideas for fancy termination, surface termination that we can do, we would love to hear them. But regardless, the system works, so you can get Purcell effects of about 10 to 20, which is kind of normal within this spectral range. All right, so I guess I will shift a little bit to the blue emitters. So it's the same material, the same HBN, but now we're going spectral shift a little bit to the blue, and I will tell you why we are going to the blue. So this has a nice history. Well, actually, so in 2021, so now we are going back into kind of COVID lockdown era. So there was a group from Detail, the group in France, they published that they can generate an arrays. I think you can see the array. Yeah, maybe. Trust me, there is an array here of single photon sources in HBN. New blue emitters emit always at the same wavelength. And as you probably gathered by now, our biggest challenge with HBN is that the emitters are fluctuating in wavelength. They're all around 600 nanometers, but still fluctuate. And you really don't want that because you really want something that is focused exactly on the same wavelengths to actually design something for them. So then we look back at the literature and we saw, oh, wait a second. There is 2019, 3 years ago, almost before that, people already measured these blue emitters, actually randomly. This is from the group of Alex Zettel in an exfoliated HBN flake. So every spot here has a blue emitter. So not always when you read something in a fancy journal that claims new is actually new. This is more for the students than the rest of us. So back in the day, we started actually looking at these emitters and we did a lot of crazy stuff like patterning UTS logo. In principle, I noticed that academics can only pattern the university logo. Nothing else somehow is going there. Or smiley faces. People pattern all the smiley faces. And so then we were just sitting on this data for no reason until this paper came out and we were like, okay, well, we should probably get going. But the results are quite nice. So you can really engineer, and I will show you now how, these defects on demand. And you can also see them both in photoluminescence and cathodoluminescence. And when you see a defect in both photoluminescence and cathodoluminescence, is really good because it means that you can excite at both sub-bandgap and also above bandgap, because cathodoluminescence, you just bombard your material with 30 kV or however CL system you have, and you still see exactly the same line. Of course, from a single, you would see an anti-bunching, and there is a lot of discussion in the literature. Why do you see bunching in CL? We can talk about it offline, but it's just pretty picture. So how do you generate these emitters? Well, you just sit with your electron beam and you just irradiate with, as you increase your radiation dose, you increase your defects, the luminescence intensity. And the important bit here is there is no annealing. Okay, there is no annealing whatsoever, and it scales linearly. And what it means that there is no diffusion limiting factor here. Typically, for most defects, there is a lot of clusters around. So you maybe have like a nitrogen vacancy, like in diamonds. So you would need to anneal to bring the vacancy to your nitrogen. In this case, there is no annealing. So whatever is that you do with the electron beam, and remember, this is a very low energy electron beam. So we don't really kick any atoms out. There's not enough energy. We only locally break maybe a bond that is reconstructed straight away. But you can generate those defects basically with very, very high probability. So the question is what they are. And so then we basically called up every person we know that can provide us with a good high quality HBN. And we did a bit of analysis. So this is going to be a bit busy slide, so stay with me. So the names of the HBN is just different types. We don't really know what the difference, but different types. So type 1A has a very strong emission at the UV. This is the exciton emission of HBN, the 6eV. And if you irradiate it with electrons, you would create these bands and you would create this 432 emitter, which is not our emitter. Okay, the 432 is not our emitter. Our emitter is always exactly at 436. Okay. Now, if you then take type 1B emitter, you would see that this has, again, a very strong exciton line. So the quality of HBN is good, but also in addition, it has these three typical peaks. These three typical peaks in HBN called the 4.1 EV defect. It is related to carbon dimer. It is one of the oldest defects that are studied or known in HBN. The theory suggests that it's just a carbon dimer sit in a boron nitride lattice, which makes a lot of sense because carbon is basically the same size as boron and nitrogen. So it's interesting that when you take this type of material and you irradiate with electrons, right? So the dashed line is irradiated, you do create our 436 nanometer emitters. Okay, so in the carbon HBN that contains carbon dimers, we always create these defects. Okay, so now let's take another type of HBN, which is very bad. You see there is almost no exciton emission, very defective HBN, and that has a lot of carbon. You see the emission here is very strong. And we can irradiate this and again create this 436 nanometer emitters. Now, we can basically take now any HBN, if you anneal them, you would get this carbon defect. So the annealing here is happening before we irradiate with our electron beam. Yeah, before, not after. After, no annealing. And we can take another defective HBN. So this is, again, no UV, no exciton emission and no UV emission, very broad, not the carbon defects, and there is nothing forming. And then we can just repeat with type 1 annealed, create this carbon triplet here, 4.1 eV, and easily create our 436 nanometer emitter. So very deterministic, very reproducible, and we now can control in which HBN material we can actually create these defects. Huge step towards actually engineering something on demand. Origin, your best guess as good as mine. Something with carbon, most likely, because we're breaking a carbon bond, most likely. But there is also an argument for the fact that this defect can create a very specific Fermi level within your crystal that will then stabilize a defect. And I will show you one example or one hint towards how we're approaching to solve this puzzle. Now, you can already see from this type of data that these defects are going to be good in cryogenic temperatures. So this is just a histogram of many of them. We only plotted about 10 here. There are a bit more here, and you can see that the distribution of lines falls within a nanometer. So it's like a terahertz, 2 terahertz maybe. And this is actually better than the best defects in diamond. So there's now a lot of hype about silicon vacancies in diamond and germanium vacancies in diamond, all the group 4 that are very symmetrical, that has no permanent dipole. This is better. So the distribution of lines is very narrow, all emit around 436 nanometers. And of course, if you then cool it down and you bring your narrowband laser exactly into 436 and you start scanning to see what is the line width, you get 2 gigahertz. So it's very good because it's 2 gigahertz stable. You see the repetition here. You scan again and again and again and again, and you always get the same line. The emitter doesn't disappear, no fluctuating fields, basically happy days. This is just as a function of temperature to get the phonon replica. And of course, when you then do a G2 measurement on resonance, you would see what's called the swings. This is not an artifact of the measurement. This is actually a Rabi oscillation, which means that the emitter is actually coherent. So, and you can, this is the first evidence that you actually have coherent emission from HBN. So if you now, and that's what the guy is doing in the lab, if you now separate the beam, delay 1 photon and let them recombine on a beam splitter, you should be able to see photon indistinguishability. So this Rabi oscillations is basically the first step towards generation of indistinguishable photons. Okay, so again, because we are working with HBN and we know how to make this type of devices, the idea was, let's see what we do with Stark shift. And so this is basically the same device with just putting it on top of a metal and capping it with graphene. So the device looks like that. That's the optical image. It's always interesting in 2D material people how they put these random lines. I once asked the students to see the image without the lines, and for the life of me, I could not distinguish the different layers. So sometimes I think they just randomly draw something and say, okay, that's there. So, but okay, just wanted to bring it out there. The results here are actually quite interesting because you will see that there is a few gigahertz linear stack shift. So only a few gigahertz. So remember the previous stack shifts for this red emissions were massive nanometers. We can shift them. This is very small, and the line width is remaining almost the same, so almost 2 gigahertz. So that's kind of tells you that there is probably no permanent dipole in the defect. But you can also do is you can actually apply a linear Stark shift, which means that you can put the flake on a kind of interdigitated mask, interdigitated pattern, and here the results are different. So here you would have the ZPL following this parabolic behavior, which means that again there is no kind of linear Stark shift, it's only a quadratic effect. So it's a very minor effect on the structure. So the structure should be very, very symmetrical. And so again, because we work with 2D materials, there's almost no geometry that will give you inversion symmetry. So typically this type of behavior is limited to defects with inversion symmetry. With 2D systems, there's almost no inversion symmetry. You need a very specific configuration of your layers to get there. And so the idea is then that the defect is something that looks like an interstitial. So an interstitial in this case is if you're taking an atom out and instead you're putting 2 atoms a little bit below and a little bit above. Okay, and this is what's called a split interstitial. And these atoms can be carbon, okay, can be nitrogen. The DFT calculation suggests that both configurations stable. Because we only work with multi-layers, there's no problem with stability there as well. And for full disclosure, we have never seen anything in a true monolayer of HBM. Okay, so that's a big challenge we can discuss a bit at the end. Now, it also kind of corroborates well with the two carbon defects because the 2 carbon defects are in plane defect, and that's known. So the 4.1 EV is in plane. And so if you break the bond and there is a carbon that can, one will go up and one will go down and will reconnect, then it is in principle a possible configuration. Of course, getting nitrogens is equally easy because it's a boron nitride lattice. So different probabilities. The only thing that we are pretty much locked in is on the symmetry. So on the symmetry, we're very confident. On the crystallographic data, exactly not so much. So still a little bit of work to do. One way to address this is really to do isotopically pure carbon, and then looking at some more signatures of hopefully some hyperfine if you can see it. The other thing I will add here is that because we only make them in this carbon-rich HBN, the kind of our, not hypothesis, but we lean towards the carbon rather than the nitrogen. And finally, I should say that people also modeled a lot about in this, like only a single carbon atom, because in principle, you could have a single carbon atom, a single substitutional carbon atom, which is an optically active defect. But in HBN, these carbon atoms are unstable, so they will cluster up straight away, even at room temperature. So both CB and CN would not be a stable impurity in HBN with optical line. Okay. How are we doing with time? Okay, good, semi-good. Good, okay. Okay, all right, so then let me then kind of conclude with the spin defects, which for many is the most important bit. And the reason why I say it's the most important bit is because, as I showed you kind of on the first few slides, that there are many single photon sources around. Unless you have an access to spin, you don't have access to memory. And unless you have access to memory, it's a pretty much useless thing to do because you can't do much with a single photon source without a memory. Only quantum key distribution, which, okay, you can do, but you basically limit it. So you need a spin. So what do I mean by you need a spin? So let me give you one slide about NV centers. So the reason why NV centers are so cool and hot is because you have this level structure, which creates a splitting in the ground state, and it has a C3V symmetry. And this splitting in the ground state is accessible by microwave radiation, so 2.8 gigahertz. Normal microwave you can buy on eBay for $1,000. And the other thing that this system has is that you can excite it with the green laser, obviously, and the transition rates through the metastable state, which is causing spin mixing, are very different than the relaxation down from the excited to the ground state. So there are two things here. One is that you can control the 0 to ±1 with the microwave, and two is the transition rate for your spin mixing, and the direct emission has the different rate. So one is 100 nanosecond, the other is 10. And what it will give you is that if you apply exactly the microwave transition, your luminescence will go down, because you will basically drive this through here, and then you would get a reduction in luminescence. And so this reduction in luminescence, it's called an optically detected magnetic resonance. It's basically an optical EPR. Okay, so it tells you exactly which spin state is your system prepared. And of course, like EPR, you can also apply magnetic field to split these levels, the plus and minus 1. 0 obviously stays at 0. And what you will see then is that your ODMR signature is basically splits, one through this transition, one through that transition, and you can see it optically. So it's basically like a magnetometer, but using optical means. So in principle, the hype around NV center is that you can have a laser and a diamond full of NV centers, and you put it on a submarine and you can map the Earth crust, because the Earth crust is magnetic. Yeah, you can do it. Do you need to do it? Not sure. Okay, so the question was, well, can you find a spin defect in HBM? And so here we go back to 2018. I was visiting the group in Brazil because UTS has a collaboration with Brazil, with a group in Manigras, I think it's called, Manigras. So, and the group there, the only thing they have, and they do it really, really well, is neutron irradiation and EPR. And so we took an HBN and we neutron irradiated it, and it became pink. This is not a false color image. It is actually real HBN, real optical image, become pink. And when you do EPR, you actually see this line, the split line, very strong. It's a spin half defect. Based on my personal research, this is the oldest EPR signature of any solid. It goes back to 1975 from Katsir. That was observed. It's, yeah, basically here. It was here from 1975. It's correlated to the OBC and the TBC. It's 1 boron center and 3 boron centers in HBN. They are not optically active, boring. Okay. However, if you keep irradiating, and to this date, we don't know why we kept irradiating, but we kept irradiating to 8 and 16 hours, you start seeing another signature, which is here and here. And so this line C is actually a spin back then we thought bigger than 1, just because of the behavior of the EPR. You don't have the symmetrical peak. And when we took the sample back to UTS, we saw that this also has an emission around 800 nanometers. Now, all these peaks are artifacts of our spectrometer. This is how you do bad science, and it cascades down the literature. We didn't realize back then that this is actually an effect of our mirror coating, because we never were working in this 850 nanometer range. So the emission looks like that. It's just smooth. Okay, we obviously corrected since then, but the emission is just should be smooth. Now, of course, when you see this coupled with your EPR and it scales with the dose, you know that you're working on an ensemble of high spin defects. And when you're doing ODMR measurement, you don't know where to scan, but you just do a sweep, a blind sweep. So we swept from 0 to 6 gigahertz. This was done in a group of Vladimir Dyakonov in Würzburg. And this was interesting because I was literally calling every single collaborator that was doing NV work and asking them, can you please do a scan for us? Because we don't know how. And everybody was like, no, we're busy. This HBN is nothing interesting. So no, and until we kind of partnered with Vladimir. And so you can see here this ODMR, because it's an ensemble, you have 2 peaks corresponding to just strain detuned boron vacancies. As you increase your kind of magnetic field, the peaks would split. Okay. And because it's an ensemble measurement, we have a whole crystal irradiated. You can go back to the EPR and actually find the hyperfine straight away. That's how you know which defect you're imaging. And so you can model boron vacancy or nitrogen vacancy, you know it should be something very simple because you create the whole crystal is basically changing color. So for boron vacancy, negatively charged, you would see 7 lines. Yeah, so basically 3N. And for nitrogen vacancy, you would see many more, which we don't see. So this is the simulation and the measurement, and this is the simulation and the measurement. So we kind of, you conclusively straight away know that you have a boron vacancy defect. So this is why in the whole defect community, it's very important to do EPR on an ensemble before you go to singles, because you know what you're working on. Of course, as I mentioned straight away, we are curiosity driven research. So we always go to singles first because it's cool, but often we don't know what we look at until very late, which is fine. So because it's only a boron vacancy, you can engineer them very easy. So this is our earlier attempt with just xenon. But more recently, you can do it with argon, nitrogen, or any focused time beam that you have. You have many of those around here. You can create beautiful arrays on basically any exfoliated flake. So this is pristine versus implanted. Again, no annealing needed because it's just a vacancy. If you anneal, they will diffuse out and the emission will disappear. And so here we started to chase single emitters because, well, you can create them and there are spin defects. Let's get singles. And so the first attempt didn't work. So you see here, the emission intensity disappears, basically vanishes to 0, but we could still never record an anti-bunching measurement. Okay, so they're just too dim, meaning that the quantum efficiency is just too low. So what do? We make bullseye and we know how to work with HBN. So we pattern these lenses. It's called a bullseye cavity, but officially just an antenna. It has no Purcell enhancement almost. It just collects more light. And you can see that you can collect much more light at around 800 nanometers. Obviously, if you design it properly, the ODMR is beautiful because your signal to noise ratio goes up. And so you can really resolve the hyperfine splitting. So this is just the hyperfine of all the surrounding nitrogens, which is nice, but again, no single emitters. Even if we implant directly in the middle here, a very low dose boron vacancy of ions, no singles. Okay, so what do you do next? You go to a different cavity design. So you go to a gap cavity. So a plasmonic gap cavity means that you have a metal and then HBN and a cube on top. And this in principle should give you the biggest enhancement that you can potentially get. So about 100 or so. So there's a PL enhancement about 100, 400, sorry, if you design it properly. So the thicknesses here is critical. And so you can indeed measure, we measured enhancements quite high. So actually the highest I've ever seen. So about 30 or so, 20, 30. And you can see this is one example where you have coupled and uncoupled emitter that you can barely see. So this is experiments that are done in a way blind. You irradiate with very low dose your HBN. You don't really see the emitters. Once you put the cubes, everything shines up, but still no singles. So our kind of aim to generate single VB centers still not solved. In parallel, there was a very nice work from Purdue who, instead of making gap cavities, they actually put this HBN directly on the microwave antenna to generate the microwaves. And they saw another interesting effect, which was an ODMR contrast enhancement. So they see now about 50% contrast in your ODMR. Now, the best measurements for NV centers are around 5% or so, 7 maybe. They see 50%. So of course, for sensing, it's great because your measurement time is going basically to a few seconds. You pay the price of the sensitivity in terms of your hyperfine. So if you want to do, let's say, some nuclear spin polarization or some spin manipulation, that's a bit harder because you see the hyperfine is lost, but the contrast is much higher. Okay, I guess I will stop here. So to wrap it up, basically, we can engineer the red visible emitters pretty much everywhere, but we don't know what they are. This cryogenic spectroscopy suggests that we can get potentially to very narrow lines, not indistinguishable photon sources yet. The blue emitters we can now engineer, and we think we know what they are. The problem with them is that they're blue. For those who work in optics, there's nothing good happening in the blue. Everything is lossy. and not optimized. And finally, the spin defects actually took off. There are many different groups now, especially in the US, that are working on actually demonstrate sensing. We also did some work with JP Tetian here in RMIT. Yeah, and so the vision is really to try and make something integrated on chip. So this is still the first, I think, before COVID lockdown, or maybe in between lockdowns. The group has now shrank to a few people because everybody graduated. So we have a lot of openings, obviously, as I'm sure you do here. Acknowledging the collaborators, findings, and thank you for your attention.
There's some questions for Igor. And I think one reason you're choosing hexagonal boron nitride is because it is two-dimensional and you can stack it to other heterostructures. And I found you have a design like capping HBN and emitter HBN layers. So since the discovery of magical angle in bilayer graphene, so my question is, do you think there is a magical angle in your system that can give very vast influence of your experiments, your emitter performance or something?
Yes, so in the group of Alex Zettel actually did it, and there is a magic angle. It's not very small like in graphene 2 point something, so you need to twist by a larger angle, and they think that this is causing an enhancement of a very specific emission at the UV. Of course, if you go to the visible defects, it's too far from any band, so you will almost have no interaction with the bands regardless of how you tune, how you rotate the flakes, right? Because when you rotate, you mostly influence the kind of the electron density of the conduction or the valence bands. And so unless your excitation mechanism or emission mechanism involve one of the bands, or unless the phenomena that you're working with involving the bands, you would see no effect. So for the visible defects, there will be almost no effect because they're very deep in the band. For the UV emission, because it's very close to the conduction band of HBN, yes, there is an effect.
Okay, thank you.
Hey, I kind of related to the layers again. So you've got like the defect layer, and then you've got the capping layer, and they're of a thickness of around 20 nanometers each. Is there any sort of specific reason you chose that, or was it somewhat arbitrary to be thick enough that it doesn't have any sort of like monolayer / bilayer effects for HBM?
Yeah, so basically when we create most of our emitters, when we create them, we work with a few layer material. When we grow, it grows to about 5 nanometers. So that's our standard nominal thickness of most of the stuff is 5 nanometers, 5 to 10 nanometers. When we want to when we exfoliate from very pristine crystals, when we want to engineer the emitters by ourselves without growth, we typically do it with a plasma. The plasma only affects the very top few layers. So that's how the capping idea came. Let's just protect with a cap. Now, the answer to the question whether it's 20 or 10 means anything, probably not. We have never managed to exfoliate a monolayer. And the reality is that every time I ask somebody if they can exfoliate a monolayer and I hear yes, I'm very curious to actually receive a sample. I have not yet in 5 years received any sample that was exfoliated by hand. There are some grown or some particular tricks, or Luha Lee in Deakin, he sent us monolayers on TEM grid that they prepared in a specific way, but exfoliation is very hard. So for us, we have never exfoliated monolayers. So we have never seen an emitter in a monolayer yet. Okay.
Oh, yeah. Are there any questions online? If so, you could unmute and ask. All right. Any other questions in the room? Yeah.
Nice talk. So if if I were able to synthesize a single layer of HBN on a metal, do you think the emission will be quenched by the presence of the metal, or?
So good question. So for nickel, we looked at a few synthesized on nickel, and their emission is there. On copper as well. But the emitters behave much better if you exfoliate. But I'm talking about, let's say, 3 to 5 nanometer growth. So because we never grew a monolayer. So if you have,
So we can grow a single monolayer of HBN on copper in
So-
vacuum, and we can look at it with the STM. But
yeah, so
Yeah.
that's the question there is whether you have emitters there to begin with. We don't know. Yeah. So we would need to run kind of some sort of a process, maybe a plasma or some sort of an implantation to try and make emitters there first and then see. And so then the challenge is for this blue emitters, we haven't seen it yet. For the spin defects, we irradiated and we haven't seen it yet. But this is, I think, because of the quantum efficiency is too low. So when we irradiate, let's say, multi-layer, we have a lot of emitters in different layers. When you irradiate a monolayer, you only obviously have the density within that layer. So the number of emitters is much lower. So the question whether it's quenched by the metal or you don't see them because you don't see them, it's because they're not there. It's a hard one to answer. But definitely we would love to have a look if you have spare samples. Yeah.
Ding ding, round 2. So when you go back to the types of like type 1A, type 1B, type 2, obviously you've got the plot of the intensities. Do you know what the relative intensities of each of those, like which is better out of type 1A or type 1B or type 2 when they're irradiated? Or do you not really see much of a substantial difference?
Actually, so it's all normalized to the main exciton line.
Yeah, that was what I was thinking.
Yeah.
It's all normalized to the
It's all
exciton
normalized
line
to the exciton
individually, but do you know what they're like compared to each other if you put them all on the same plot?
No, we don't. We don't know. Yeah, the answer is we don't know. But the brightness of those single defects is relatively low, so maybe around 30, 40,000 counts per second. So the visible ones are in the hundreds, maybe 10 times less. But kind of eyeballing it from the data sets that we had, I don't think there is much difference in the intensity of them as a function of which type you make.
Okay, so it's like consistent between types. There's not really many sort
Very
of change.
relatively
Cool.
similar.
Cheers.
Brightness. So the spin defect, you were putting that into optical cavities just to try and see singles, or because
Correct.
is
yes.
it how bright is it sort of?
It's very dim. So the quantum efficiency, so it's like the brightness that really depends on how good is your optical setup.
Yeah.
But the internal efficiency of this type of defects is probably about 0.5%, probably less even. The reason is it's in the, as you go closer to the IR, you have more phonons, blah, blah, blah. So you have more non-radiative relaxation. So when you put them in cavities, of course, they're bright, but they're still not as bright as a single. So when we made antennas for this visible emitters, you get basically 10, 15 millions per second easy on your detector through the collection. So here, much worse, 100 times more worse.
Really nice talk. Just on the control of the charge state, can you go to the slide with the silicon carbide results? Like, you know how you were mentioning in this work, they're actually trying to create a PIN junction. Have you thought about using like a top layer of graphene and a bottom layer of graphene is actually like that PIN junction to stabilize and really fine tune that?
And then control the graphene PNN by doping or by some surface
Yeah,
manipulation?
exactly.
We haven't done it. No, we haven't thought about it either. We tried only once. I think it was nickel oxide HBN graphene, and we didn't really see much. But the reality is that we don't really know if our graphene is P or N type. Like we don't really know how to do these measurements properly. So what we rely on is we just make the device and we measure IV curves from this type of devices and we see the IV curve behavior basically. But we we don't check the graphene before to know if it's p-type or n-type.
And one follow-up question to the structure. I mean, I don't know whether this is the case with HBN, but have you considered putting the HBN capping layer between the SiO2 and the emitter layer? Because often like there's charge traps in SiO2 or just spatial inhomogeneity.
Yes, that we did. We did capping under, over, played with the capping layers. That we had no effect on the results.
Oh, that's good. Yeah.
So I mean, electrostatically speaking, this is not a good device. It just fit for purpose for the emitter manipulation, basically. But electrostatically, it's definitely not optimized.
Let's thank you, Igor, again. That's fantastic
Thank you.
talk.